So my name is Alok. I'm the first author of this paper, and this is kind of like a little tutorial on my project, really. My idea is that the research community, you guys, can download this, make your own scenarios, and really have fun with this. So I'm not going to go into too much detail on how the algorithm really works, but essentially these robots are planning their paths. They're basically planning their position and velocities at time steps in a short forward time window, and they negotiate these trajectories with their neighbors. We use Gaussian belief propagation, or GBP, as a way of performing inference on the sparse factor graph that's created. But please go ahead, watch the video, read the paper. I'm sure you'll find it interesting, or I hope, anyway. So I'm just going to begin firstly by kind of going through the code, but I'm going to focus on the areas where you guys as researchers might want to make some changes or modify, and then I'll show you how to make your own scenarios, make your own obstacles, and yeah, really have fun. But let's first begin by just downloading the repo and seeing how we just run it. Okay, so in this section we're just going to download the code. So you can go to alpatia.github.io/GBP Planner. This is a project page where you can see the actual video itself, as I might have mentioned before. But that takes you to a link to the GitHub page itself. I'm assuming you have familiarity with how to clone a repo, but just in case, you go to code, you copy the actual URL, and then in my terminal, all I need to do is do git clone and paste the URL. Don't forget to do recurse submodules. So this is because the actual repo has a submodule called raylib, which is for the graphics, and if you don't do recurse submodules, it's not going to be initialized properly. So I'm just waiting for it to now download. Okay, so that's all done now. I'm going to go ahead and CD into the GBP Planner. Okay. Now all I need to do is create a new directory where we're going to build our program. So just make dir build. Then I'm going to change directory into the build and run cmake. ... Again, this is all the instructions here are on the GitHub page itself. Finally, I'm just going to do make. And you can just run make by itself, but you may find that on your computer you can make use of the multiple cores and do -j followed by a number. So on my computer I like to do J8, and that does seem to normally work a bit faster. So now it's just going to make the actual whole code itself. Now again, depending on what else is running on your computer, this may take less or more time. Okay, so that's done, and I'm already in the build directory. So all I need to do to actually run the basic demo or the basic simulation is /GBP Planner. And as you can see, this is one of the examples. It's that easy. So this is the circle experiment. Of course, I'm doing a screen recording, so there might be a bit of a lag here. But essentially, that's all there is. So that's it done, right? Press escape, and if I want to run something else, a different configuration file, for example, GBP Planner --cfg, and then I have my path to the actual config file that I want. There we go, and it's that easy. Okay, so now in the next section, I think I'm going to go over just how to play around with this. Okay, so now I just want to show you how to run the simulation and how you can interact with it in many different ways. So I'm going to use the two-way junction example here. So just /GBP Planner, as you can see on the screen, and that loads up this simulation here. The first thing to remember is this represents the whole world. This big square represents the world domain, and that goes from -world size over 2 to +world size over 2. X is positive to the right, Y is positive downwards, just like in the standard image sort of setup. Now the main thing here is on the bottom left, there is the time, and the bottom right is the frames per second. To pause the simulation, you can press enter, and that also restarts it. If you want to bring up the help menu, that will tell you all the ways that you can interact with this simulation. So the main thing is when you want to change the camera view, I'm just using my mouse wheel here. I can zoom in and zoom out by scrolling. I can click and drag using the mouse wheel to pan around the image, and Shift plus the click and drag of the mouse wheel can rotate it. So very straightforward, and then you can get some nice views here. Now the robots are red, green and blue in this scenario. Green ones go straight ahead, blue ones are turning right, and red ones are going left. If you want to see their planned paths, you press P for planned paths. Now since the robots are always moving towards their next waypoints, you can press W for waypoints to visualize these waypoints. These are the little cubes here. And finally, by pressing R, you can see the robot-to-robot connectivity, or the inter-robot factors. So do have fun, play around. If you get stuck, you can just press H, and that will tell you all these different ways of interaction. And finally, to exit the simulation, you can just press escape whenever you want. Okay, so now I just wanted to run you through the code, but I'm going to focus more on the bits of code that you as a researcher might want to modify or add your own cases to. So I'm going to begin by opening up the code in VS Code, because that's just my editor of choice. And here we have started with the main.cpp file. You don't need to change this at all. Just wanted to show you that we begin by setting the random seed, reading in the config file. So the config file basically will contain all your little parameters that you might want to change. So let's have a look at that first. Okay, so the config file will be in config, and you can even create your own config file later. So the things you might want to change are in simulation parameters, or maybe GBP parameters. So with simulation parameters, you have the random seed, the seconds per time step, the time or the number of time steps after which the simulation automatically ends. You have some other things such as the number of robots, the look ahead time, and you also have the name of a formation. So here we have circle, and in a moment we're going to create our own formation. So let's call this demo. So right now this is not going to work, but we'll create it later. And in obstacle file, this should be the path to whatever image that you want. So the image containing obstacles, which are in black on a white background. And then in GBP parameters, these three, the sigma factors, they are the strengths of all the factors, the inter-robot factors, the dynamics factors, as well as the static obstacle avoidance factors. And finally, you have the number of iterations per time step, again, which you can change. So all of these different parameters are actually read into the globals class, globals.cpp. Don't worry too much about that. The only reason I use this whole JSON thing is so that you can change your parameters and play around with the simulation without having to rebuild the code every time. So that's the config.json. You can create your own one depending on your own demos. Now we're going to go to the simulator.cpp, because you might want to make some changes here. So let's just go to the top. One thing to note is, because it's a distributed algorithm in which each robot is always on the lookout for nearby robots, but we're demonstrating it here on one CPU, so it's kind of centralized. So we use this KD tree, which is a really cool data structure. If you haven't heard of it, go and look it up. It's really amazing. We use that to store and update the robot positions. Then we can really do fast radius searches or nearest neighbor searches, stuff like that. And I think the other stuff I've commented, it should be okay. I just wanted to let you know, this is just research code. This is not optimized code. You may find issues with the coding standards of comments, but if you have any suggestions, please feel free to reach out. Do a pull request, yeah, why not? Okay, so if you want to create your own simulation or your own scenario, apart from the examples, you go towards the end, go to this function called create or delete robots, where vaguely, in general, you can see that it's if-else statements, depending on global.formation. So if you remember in the config file, we just created a new one called demo, so we'll create that in a second. But just to show you how this works, there is a vector called robots to create and a vector called robots to delete. And we just append to that vector, because this function create or delete robots is called at every time step. Now, if the formation is such that you don't need to create new robots every time, then this new robots needed flag should be set to false. Otherwise, at each time step, when you enter this function, the robots are going to be created. And you may not want that. So just as an example, in the circle formation, we set new robots needed to false. Then we set some other parameters, and we have this loop for globals.num robots, which is however many robots we want to create. All I'm doing here is I'm creating a starting vector, which is basically x position, y position, x dot, and y dot, the velocities as well. And I append them to this list of waypoints. So I just want to reiterate that each of the waypoints in here is 4-dimensional, x, y, x dot, y dot. And finally, I append to the robots to create, a shared pointer to the new robot that I've created. If you're not too familiar with C++, don't worry, you can just copy and paste this essentially. That's all you need to remember, waypoints. Create this waypoints list. You can have as many waypoints as you want in there, because remember, robots, they initialize at the starting waypoint, and their horizon state, that's the furthest time step they're trying to plan to, is always initialized towards the next waypoint. And as soon as that next waypoint is reached, the horizon states start moving to the next waypoint after that. Very simple. Just to note here, for the junction case, new robots are created and being destroyed at every time step, which is why I set the new robots needed flag to true. Okay, so now I'm going to create a new scenario. So let's say in this scenario, well, firstly, we're going to call it demo. So I'm just going to copy that. This is all live, okay? I've not done this before. Just wanted to hopefully show you it's not that, difficult. Firstly, I just want to create this at the start. So I'm going to say new robots needed is false. Okay, I don't want any more to be created after this one. And then I want to initialize my starting vector. So starting equals eigen. So I'm using the eigen library. This is kind of like NumPy, but for C++. And you can create a new vector, a 4D vector like this. Okay, that's a starting vector. Do the same with an ending vector. Why is this complaining? Very interesting. Have I forgotten? Yes, I've forgotten a bracket. Alrighty. Just forgotten a double semicolon. Anyway, yeah, so I've created a starting and ending vector. I will now add them to the waypoints vector. I'm just copying it from above. No need to get all fancy. And then I basically am gonna create a new robot and push that to robots to create. I'm just gonna say the color should be red, which is kind of like 0. This is an HSV, right? So don't worry too much. You can select your own color. Look at the Raylib guide if you want more information. So as it stands, I've only created one robot. So let's say we want to create more. Let's say we want to create num robots. Then I need to do that for every robot. So for int I equals 0, I less than globals.num robots, I++, indent. Okay, yeah, this is kind of fun actually. I've not done this before, live editing. Anyway, so this is now going to create lots of new robots. I don't want them all to begin and end at the same location. So what I'll do, I think, I'll set random values, okay? So I'm going to do multiple at once just so it's a bit easier. So I'm modifying the X, Y for both, starting and ending. I've got a function called random number, or random int actually is better. It doesn't have to be an int, but why not? And I'm going to say, because my world, remember the world goes from minus global's world size over 2 to plus global's world size over 2. That's what I'll do. Minus global's dot world size over 2 to global's dot world size over 2. This is going to complain because the eigenvector xd expects a double. So all I'm going to do is, again, this is, don't worry too much about this, and my mouse is behaving quite weirdly today. Okay, I'm just going to times this by a double, so it just kind of shuts up like that. Right, so just to recap, for each new robot, I create a starting and ending vector, which is has 0 velocity, x dot y dot is 0, and a random ending place. I create a list of waypoints, and then I create the robot and add it to the robots to create. That's it. Okay, so I know I explained a lot, but you can actually do this a lot quicker than that. So I've just opened up the terminal in here. I'm going to cd into the build directory and make again. Fingers crossed, it should all work fine. And yeah, now I'm just going to, oh, one thing we did forget was change this circle to demo, because we've just created that. Now remember, the default loads config.json, and so in my config.json I've selected my formation to be demo as well. Just need to make it again, and then we can just run it by /GBP Planner. That's basically it. So just to show you their planned paths or their waypoints that we created, they're just heading to those waypoints. Right, so very simple. What if you want to do dynamically changing waypoints? So right now, all we did was we selected a starting waypoint and an ending waypoint, and nothing really happens once they reach that. So if you did want to say, okay, well, when the robot reaches its, waypoint, I want to randomly create a new waypoint, and that can easily be done as well, but we just need to go into the robot.cpp class. So I wrote this code for the paper that we did, so we weren't really considering this kind of stuff, but it's quite generic, so please feel free to have a go. So in robot.cpp, I'm going to the update horizon function. And all I'm doing here is, if you notice, what's happening is there's a vector for new velocity and new position. And all I'm doing is at each time step, I'm just updating the velocity of the horizon state to point towards the next waypoint, or basically what's at the front of the waypoints queue. And once that reaches the waypoint, I pop the waypoint from the queue. So instead of popping it from the waypoint from the queue, why don't we just modify that? So waypoints dot front, that's the next waypoint that we're heading towards. And I want to change the x coordinate of that to a random, let's say random number. Now the randint function is part of simulator, so you need to access the simulator class like that. Random int minus globals dot world size over 2, globals dot world size over 2. And I think this wants it to be a double, so I'll just times that, just in case. And I want to do the same to the y coordinate. Yeah, I think that should be fine. Yeah, now before I make this, I'm just gonna, well, I can make it now actually. Make. And to just make it easier to visualize, to demonstrate to you guys right now, in the config.json, I'm only going to create maybe one robot. Okay, so that hopefully what you can see, I run it now. with the waypoint and the plan on. So once he reaches the waypoint, or it reaches the waypoint, sorry, the waypoint should change, or a new one should be generated. And that is exactly what you see happening. So guys, I hope you can see that you can define your own sort of functions or waypoint generations. Really do what you want. The code is, feel free to change it. And I'm really excited to see what new things you guys can do. Okay, now you know how to create your own simulation, your own formations. Now I'm just going to show you how to create your own obstacles. So all you need for this is a white background, and any obstacles you want, you can describe them as black in color. So maybe let's draw a nice little smiley face. There's no really mistakes here, kind of channeling my inner Bob Ross here. Smiley face, there we go. You want to see a circle? Let's do a circle. Ooh. Okay, and maybe a rectangle as well that I want to do in full black. Like that. Amazing. Maybe one over here and maybe one down there. Cool. I've saved this as demo.png inside the assets and images folder. So this should be okay. Now, as it stands, that's not enough. What we need to do is create a distance field. So inside scripts, you can see that there's a function called create distance field. For the purpose of this demo, I've just created a little demo file here where you read in the image, need to convert it into the PIL format. You apply the function and then you write it to file. And so you run it and see it's blurred. That blurring is kind of like a distance field. That's all we really need. Great. Just to check, we need to update the obstacle file path, which is correct. It's demo.png. And now when you run it, oh yeah, we want a circle formation, maybe 5 robots. Let's see. Yeah, and you have the stuff there. These are nice little obstacles. And you can see that the robots are avoiding them. So, you know, great. All right, so hopefully that was helpful to you guys. If you have any other questions, do feel free to reach out. And also, if you want to actually contribute to the code, do some pull requests, feel free. This has all been research level code. It's not really software engineering. So undoubtedly, there are lots of optimizations we could do and speed it up. So I look forward to working with you guys and post on Twitter. I want to see how we can really improve on this. Thanks.